to find the moment of inertia of the disk about a diameter. I'm just going to kind of walk by and check you after each step. Because I can do this, and I'm sure if you watch me, you'll go, yep, that makes sense. Yep, that makes sense. But until it's you, it's really not going to work out. Now, I want to give you a huge hint here, though. If you really want some success here, don't draw this the actual size of a coin. Take a moment, draw a nice big circle on your paper. You need reference. You need to be able to write stuff in there. And if yours is this big and you're trying to do some stuff in there, you're going to be disappointed. Now, you don't need a whole circle. A section of a circle will do. You know, I can zoom in and zoom out, but as long as you have a section of the circle, like a quarter of it, you'll be fine. But draw it big enough so that when you're trying to point to it using a coordinate system, you can easily recognize where the object is and use the DRs and X's and all that to define its size. So let's have some common themes here. Let's say that the object has a total mass of m and that the size of the disk is radius capital R. That way we have common points of reference. And in addition to that, I'm going to draw another diameter in here to kind of represent, you know, a starting point. So we have some places upon which we can base our measurements. Now, again, just a brief reminder. I gave you a set of steps, and we talked about circles and squares in the hopes that you'll be able to apply this under unique circumstance. This is a new circumstance. We are still working from the idea that this is a summation. And our summation is going to have three parts to it. The summation is going to include something that represents the mass of a single piece of our object. That's the dm. Something that's going to represent how far away that piece is from the axis of rotation. That's the r squared. And something that's going to tell us how we can add up the first object and the last object of the piece. So our first piece and the last piece of the object. So step one, draw a square that represents a piece of the object somewhere on the object, somewhere in the middle. Line that piece up with the appropriate coordinates you're going to use. That's step one. Let's see what you guys do. So say it again. There's two possible ways to draw your box. One lined up with X and Y, and one lined up with the radius. And you want to try and point to the corner of one of your boxes. So either using polar coordinates or rectangular. Now I should walk by and look at your stuff, but this shouldn't have taken you very long. So did you point to it by going over a distance X, then up a distance Y? That will do it. That will point out that box. Or did you do it by sweeping up some angle theta and going out? Oh, that's not great. I think I'm going to redraw the box to line up more with the radius. There, just sweep out some angle theta, then go out a distance r to get to the first corner of the box. What we're trying to do is come up with a set of variables that can be used to point at every box on your object. So X and Y, we can point to every box in the circle by using X and Y. And R and theta, we can point at every box in the disk by using R and theta. You just need to choose one of them. Now there is a better choice. And then I told you about the better choice on Friday, but we need to get this far. Because the next thing I asked you is, can you figure out how to select every box on your disk using the two variables you've chosen? Again, there are better choices than others. For example, I can use X and Y. There's no doubt I could use it. Clearly, I have gone to this box and found it. The problem with using X and Y, and there is a problem, is that let's say I go out a distance X1. I go all the way out to here. Then if I want to point out all the boxes that can exist that far away from the origin, well, then I can go up this high and similar distance downwards. But if I choose this to be X2 right here, then the distance to the last Y is different for this value of X than it was for the first value of X. I would need to know what my limits for Y are going to be with every value of X I choose. That's hard. It's not impossible, because you guys who have had math know there's a formula that relates X and Y for a circle. But it means working that in somehow to figure out the limits of all the different X's and Y's that there are. There is a better way to do this, and that is perhaps to use the polar one instead. And the reason why I would use the polar one instead is because if I choose theta 1 like this, then selecting the different R's starts at 0 and ends at the last one. And if I choose, say, theta 2 to be here, R still starts at the middle and ends over here, meaning R always begins at 0 and ends at the edge of the disk. For every single theta, that will be the same. We don't get that if we use X and Y. For every X, there's a different range for Y. So what I said on Friday, and what I'm trying to reiterate here with your selection, is pick a coordinate system that is related to your shape. Things that are squared off, use Cartesian. Things that are circular, use polar. Now, I'm purposely using something that's round because there are coins and you can spin them. And so it seems reasonable to use something like this. But also, I wanted to use this one because I know it's not on any chart. So, ready to keep going? That's what I want to do next. If you've pointed at the box, and for all of you who use Cartesian, I'm just going to tell you, we're not going to do that. We are going to use the polar. And Cartesian is easier for the area, though. It's just dx and dy, the size. Let me make sure I say that. If we were able to use Cartesian, finding the size of our box isn't so hard. Because our next step is to recognize that our box has area. We want to find the area of our box. If we had left it Cartesian, area for a box is length times width, or base times height. It's pretty easy to find the base and the height, meaning the base is just a little further in the x direction, and the height is just a little further in the y direction. My area would just be dx times dy, length times width, or base times height. The problem is that, again, x and y don't work really good for us. So we're going to use polar. We need to do the same thing there. So that's what I want you to do. What would you use for the area of this box? What would dA be? And you're multiplying two things together, length and width. Figure that out. Those of you having trouble getting started, you're trying to find a way to write how long this side is. And you're also trying to find a way to write how long this side is. And you have to use your coordinates, r and theta. So how many of you think you have it? It's not very many. And that makes me a little nervous. But I don't want to wait that long. This isn't worth it. Now, I want you to be able to do this. But... All right, let's talk this side first. Is there a variable that we're already using that makes sense for how big this side is? However, what do you think? So dr means a little bit more in the r direction. Does that make sense to all of you? That's what I think I would use too. It's a little bit more in the r direction. And that's how long that side is going to be. Now, somebody in fourth period said, well, can't I just make both sides the same? Can't I say that this side is also dr? Just make it the same width. That way it's a square. The answer is no. And it might not be clear why, but you can only go in the r direction, the direction that r points. So dr can't point this way. So I can't use dr here. I can only use it here because r already points in that direction. So if I want to find a variable for this width, I have to use something that points in that direction or already goes in that direction. And here's where I tried to remind you guys to think of this as like a compass. You know, one that you could use to draw a circle with. How many of you have used a compass to draw a circle? Okay, so 3/4 of you know what I'm talking about. So you put the pointy end at the center, and you put the pencil end down over here. And then what do? You move it a little bit. You rotate the degrees, whatever amount you need. If there's a whole circle, you rotate it 2 pi. We don't want that much of a circle. We want just a small amount of a circle. So this would be r d theta. It's a small amount of a change. And it's in the direction of theta, so we're okay. We're using d theta, and that's the direction d theta would go. Yep.
I understand the d theta, but where does the r come from?
Part of it is because the size of this length would be different if we were down here versus over here, right? Because it's an arc length. But also d theta isn't in meters, and we need something here that's in meters to give us an area. So we're actually using dx equals delta theta times r, the thing that would give us, you know, linear from polar or linear from angular. You're welcome. Now, this defines the sides of our box. It gives us the length and the width. The area of our box is the product here. So dr times r d theta is the area of this box. In the same way that that's the area of the box if I use Cartesian. And this shouldn't be a big surprise. When we did the disk before, we got the exact same thing. These are the standard summation notations for polar and rectangular. I don't want to say it like that, but anytime your thing is circular, you would use dr times r d theta. Anytime your thing is rectangular, you would use dx times dy. You wouldn't have to do this whole thing all over again every time. All right. You need to do something else for me now. And this is focused on what we're doing here. This is for the circle. I want you to come up with a ratio. that could be used to find dm. Remember, this is all about replacing dm with something else. This box has a mass of dm. The box has a mass of dm. That's a piece of the mass of the whole object. So you need to make a ratio now. And I don't care what ratio you use. We talked about two different ratios on Friday. You could go mass of the piece is to the mass of the whole as area of the piece is to the area of the whole. That's fine. Or you could go mass of the whole thing is to the area of the whole thing as mass of a piece is to the area of a piece. Pick one. You need a ratio. A ratio has a fraction on both sides. So pick your ratio. All right. That's really all the time I want for this because we've already done this part too. It's been a couple days, but we've done it. I'm going to start by saying the mass of a piece is to the mass of the whole thing. As the area of the piece is to the area of the whole thing. That ratio works. Now, the other ratio would be the mass of a piece is to the area of the piece as the mass of the whole thing is to the area of the whole thing. I don't care which one of these you use. They're the same. They're still adequate ratios. I like this one best because it's in terms of density. So if they give you a density, you can substitute right here. Remember the problem that I just showed you a minute ago? They gave us is going to work for you because ultimately you need dm by itself. So whether I choose one or the other of these, dm is going to be the same. It's going to be m over pi r squared dA. Now, we have something we can substitute for dA. And you should do that now. Yep.
Did you post a video of what you went over on Friday?
Yep. On Friday, actually. So we've done quite a few steps here. And this is where I told you that your steps are going to branch. There's the first step where you find dm. That's part of the branch. But then you're going to have to go back and you have to find r. Now, I've got a lot of people having other conversations. I've seen like 5 people who are way involved with something on their phone. Look, you're annoying the hell out of me. If you want to be here, go. I need you focused. And if you're talking about this, great. If not, I need you to hear this next statement. What?
He was asking about if you posted the video. I didn't see a video and I just checked it.
Then I'm a liar. I'm sorry. I guess I got busy doing something fun on Friday. I encoded all the videos. Must not have uploaded it. But to be honest, I'm not going to stop and check right now. And you have to first get DM, and that's what we've done. And I'll say it again. We are repeating the disk. We did this all already. This entire thing was done about a week ago when we did the disk in class. What we're doing now is different in that although we found dm, and we're going to use dm, our moment of inertia has 3 parts. dm is only one of the 3 pieces. And we need to find something to put in for r squared. And all day today, I've had people really have difficulty with this, and I'm trying to stop and slow everybody down and be aware that R is used for multiple things in this class. You have to know what each R means in every one of its forms. And the R we're using right here is different than the R that's being used right here. Those are 2 different R's. The R that we were using as the placeholder on the disk is the placeholder for polar notation to point to something from the origin. The R that's in this formula is the perpendicular distance from the axis of rotation to where our piece of mass is. So stop right now and draw an arrow representing the perpendicular distance from the axis of rotation to your piece of mass. Piece of mass here, axis of rotation here. I need a perpendicular line there, right? So that seems perpendicular. This is what's being meant here. When we did this the first time, the R's were the same because we were going from the center of the object to our piece of mass. But in this one, we're not spinning it that way. So our R has to be from the axis of rotation to where our piece of mass is. I'm sorry, do you guys have your hands up? Okay. Now, you need to find a way to write the perpendicular distance in terms of this R and this theta. Because everything has to be in the same units, in the same coordinates. R means something else here than it did here. So look at the geometry. There's probably a geometric way. And just to help us out, because I need another way of writing, I'm just going to put a little perpendicular symbol here. Just to separate it, to make it different. Because I have more than one R. This R and that R. Now, this is just trig. It looks like this is going to be R cosine theta. That's what it looks like to me. I just dropped that little dotted line there to make sure I had it aligned with the angle correctly. You could have also recognized that this angle here is also theta, but I have all sorts of stuff written up there, so I didn't want to make it messier than it already is. So there was 3 things that had to be filled in. There's something for dm, there's something for r squared, and then there's the limits of my my integral. I have found something for dm. I have found something for r squared. I believe I can assemble my integral now. And like I said, none of this is in calculus, so folks in calculus don't have an advantage here. So, assembly begins. in the first parentheses, I'm going to put the r squared. R cosine theta squared. In the second parenthesis, I'm going to put all that stuff I have. It's supposed to be dm. I'm not even sure it's going to fit in there. Do my best. So m over pi r squared dr r d theta. Now, I would start to do my limits. Remember, tell it where to begin and where to end. Except, we've got a problem. And this is where the people in calculus realize there's a problem. And the people who have not had calculus before have more difficulty. They know immediately to look for the dr or the d theta, the d something. But they're concerned because there's two of them. And that's not covered in Calc BC. It's covered in Calc CD. And there is no such thing. It's covered in Calc 3. So what do we do? It's not that challenging, but it will scare some of you. We have to add twice. We have to add for all the stuff for r. We have to add all the stuff for theta. The object's two-dimensional. So we have to sum in 2 dimensions. It would be the same if we had Cartesian coordinates. So we'd have a sum for x and a sum for y. Now, we're fortunate in that we have a shape that has lots and lots of symmetry. The range for r and the range for theta aren't relying on each other. Meaning for every theta, r starts at the same place and ends at the same place. Or for any one r, I can pick any angle and get a box. That's convenient. It means that these two things aren't related to each other. Now, other shapes, that wouldn't be true. So, and they're not related. So here's what you'll do next. You will take anything that has nothing to do with r and theta and bring it out front. That's easy. Then you'll separate this into 2 parts. One part collects all the stuff with r, and one part collects all the stuff with theta. Now, just to be quite honest with you, this, still the hardest part. Assembling the integral, still the hardest part. What we're doing here, it's not the hardest part. Of all the things that are worth points, assembling the integral gets you the most points. 2/3 or better. Calculating the integral, doing integral calculus, 1 point. And you're all in the same boat when it comes to assembling the integral. That part's tough. I look across all that and I notice that there are 3 r's, so r cubed, right? There's r squared here and an r here. So I get r cubed. I look across the whole thing and I only see theta once, cosine theta squared. That's all I see. Is that all you see? Now, I'm not going to make this part tough. We did this already. We're going to go all the way around the circle. We're going to go from the inside to the outside. However, I think you're done here. People in calculus and people in this class can do this one. But probably only people in calculus can do that one. And even then, if you're in AB, you don't know what that is. You can look it up on a table, though. All right. a pinwheel. Something like that, a fidget spinner. We wouldn't be able to make the assumption that every theta has the same range for R, because it doesn't. Every theta would have a different range for R. I'd probably have to know what that is. This would be a lot harder. Could still be done, but I would probably have to need to know some things about R and theta. We would have had the same problem trying to do the circle with X and Y. X and Y are related. We'd have to do something about that. However,